Now let's talk about motion. So in motion, I have told you about velocity and how velocity and acceleration relate to force. So velocity, I said, if this thing is constant, then that means there is no acceleration. And I said, if it is changing, then there is acceleration. And in, I think it was the very first video I did, I kind of defined for you what these terms were. So let me be a little more explicit this time. So let's remind ourselves that velocity is, let's see, a change in position with respect to time. So explicitly, I can write that velocity equals a final position minus initial position, because this little delta always means final minus initial. Sorry, that's an initial. Over the amount of time that took to get there. Cool. So with this one, this gives us an average velocity. It says that on average, looking at my final minus my initial position, or displacements rather, that when I compare that to time, I'll find out what my average velocity is. So if you've ever, and now with the day of Garmin, very few people do, I suppose, have used or tried to predict how long it will take you to get somewhere. When you do that, what you're looking at is an average speed. In this case, an average velocity, because remind ourselves that our units for this are meters per second, and that velocity is a vector quantity, which means that I have both magnitude and direction. So acceleration then is the change in velocity. So I would have something that is the change in my velocity with respect to time, with the amount of time that change took. Well, that gives me acceleration. Or I can write it as acceleration is then my final velocity minus my initial velocity divided by time. So this might feel a little redundant, but if you look at this then, what this is saying is that if my initial velocity is the exact same as my final velocity, then my acceleration is 0. So that means that I am not changing my velocity, therefore I have no acceleration. And this has units of meters per second squared. And if we look at that, this top piece is meters per second, that's my velocity, divided by time. Well, that's where that squared comes from. So I have a unit of meters per second over seconds gives me meters per second squared. And displacement is just this thing we can use x as. Displacement can be in the x or the y. X is just really this kind of standard variable that we use. So don't freak out about it. These things apply to both the x and the y directions. But right now, let's just kind of focus on that. So displacement is just your position. We are comparing a beginning position to an end position. So if I am, the old one is I'm walking my dog, and as I'm walking my dog, I'm going in a straight line. And here's my dog. It's a big dog compared to me. It looks kind of more like a beetle. But as I'm walking him, if I take him off his leash and he starts doing all this thing, which if you've ever seen my dog or you hear him in the background, that's precisely how they behave in real life. All this squiggly, ugly mess means nothing in our physics kind of view of things. What matters is that I and my dog started here. Here is my x initial position. And then if I walk in my straight line like I wouldn't be following him all here and there. I'd end up here, and this is my final position. So the biggest difference between displacement and distance is that when I travel a distance, I would measure all of these squiggly lines. Displacement only cares about what my final looks like compared to my initial. What happens in between doesn't matter. So it's kind of like why up here then, if I'm looking at how long it will take me to travel from, I don't know, from Western Washington University to Eugene, Oregon. You know, if there's not much traffic, It's pretty much going to go in a straight line. I mean, it's a little bit of dog leg going there. But most of us will get impatient. You hit Seattle traffic, you hit Olympia traffic, and you're like, oh, get me out of the car. And so you get off the freeway, and then you go eat, and you do all sorts of things. But if I'm looking at how long it will take me to get there, what I do is an average of the time spent moving. So my displacement becomes just the Western Washington University to Eugene, Oregon. That's my displacement. And the amount of time I get there is the total time it takes. So in that case, if I'm hitting traffic and I average everything out and I get off the freeway and have lunch or breakfast or whatever, and then I get back on the freeway and head home, or head to Oregon, then it's not very exciting, but I have a lot of time over that same distance. If I go no traffic and get there, then my average velocity is going to be a lot higher. If I'm doing this kind of thing getting there, then my average velocity, you would like look at that and be like, okay, so I'm going on average 35 miles per hour over that amount of time, and then you cry and decide to fly. So that is my displacement. We look at beginning and end only, and in general, the best way to think of these things is an average. And I'm going to talk about instantaneous in just a minute. So if I look at this graph, because this is really the best way to visualize what these quantities are, I look at this and I'm like, okay, so this y-axis here is my velocity. You see, I have a positive and a negative. So reminding ourselves that, that velocity has magnitude and direction, while a negative velocity just indicates going in a negative direction, as I have defined it. So I could call this moving to the right, and if I'm going negative and on just a straight line path, then negative would mean I'm moving now to the left. That's all. So at this point here, I look at time equals 0, so this would be like t equals 0 over here. At t equals 0, I'm starting off at 10 meters per second. Does that mean that I have developed a special machine that suddenly gets me there from 0 to 10 instantaneously? No, that just means at the time I hit my stopwatch, I'm already traveling at a positive 10 meters per second in what I've defined as a positive direction. So I'm starting at 10 meters per second, and at 10 seconds, let's see what happens here. Something happens. I go from a constant velocity, and if I look at this graph, let's see, this would be t equals 0 and v equals 0. I'm slowing down. So I'm going from this 10 meters per second, kind of following this thing, and I'm slowing down. And so I hit this x-axis, so time here is 20 seconds. And that means that I've slowed down to a stop. So if I've slowed down to a stop, and the negative sign means that I am now going a different direction, then you can think of it either as two ways. Like if you have one of those fancy lawnmowers where you can like spin on axes, you could be heading forward, but going back from whence you came. Most of us don't have fancy lawnmowers like that. So this would generally mean if I'm traveling and I've come to a stop, but now I've hit reverse and I'm going in the negative direction. So this would be, I get to some spot, I'm slowing down, but a positive velocity. And now I'm going in the negative direction. So this again, just be like going to the left. I'm sorry, if I call, let me be specific. If I call to the right positive, then this is moving in the positive direction. I'm above the axis. I come to a stop. This is negative. So this means I am now moving in a negative direction. Cool. So now let's talk about specifically what we can get from this graph. So these things here, hopefully, maybe, when I look at this, I'm like, okay, this is a velocity versus time graph. So this is something like this. Because remember, slope equals, let's see, what is that? Rise over run. So my rise is velocity. So my rise is velocity. More specifically, the change in that velocity. And my run is time. If you want, you'll see it written like this, the change in time. A lot of us don't. A lot of us just leave this as t, simply because I can take t equals 0 from any place. So I'm just looking at the total amount of time that was. So my slope is rise over run, the change in velocity versus time. So I can look at from like 10 to 20. And what I'm seeing, let's see, what am I seeing? My change in velocity for 10 to 20, let's do a different color. My change in velocity for t equals 10 to t equals 20. Let's see, what is that? So at 20, my v final is 0 meters per second. Let's see, minus my initial. So here I look at it, I'm going 10 meters per second, so minus 10 meters per second. And if I want to do my slope, what do I end up with there? I end up with a change in velocity with respect to time. So I can do this. My v final minus my v initial gives me a negative 10 meters per second divided by the time. So this total time, 10 or 20 to 10 seconds, I'm sorry, 10 to 20 seconds would be just 10 seconds divided by 10 seconds. Well, let's see, that gives me just negative 1. Well, meters per second divided by seconds, the seconds are both on the bottom. That makes them squared. Negative 1 meters per second squared. Holy moly, look at that. That is acceleration. So the slope of a velocity line gives me the acceleration. This is a negative slope. That means my acceleration is negative. In this particular case, I'm slowing down. So now let's look at what happens down here though. Here, from t equals 20 to t equals 30, what's going on there? I have a negative velocity, okay? So let's see, at t equals 30, I'm at this, my velocity, my change in velocity then is, let's see, I end at negative 10 meters per second. So my final velocity is 10 minus my initial velocity, which was 0. That's that. And then I can go here, how much time did that take? That's 10. Oh, so that shouldn't be much of a surprise. So again, I'm getting negative 1 meter per second squared. Like a dv dt. So that feels like exactly the same result. In fact, it is. But there's one very important distinction to make here. A negative acceleration does not always mean you're slowing down. Even though these answers are exactly the same, this one is negative because I ended with a negative velocity. This one is negative because I started with 10 meters per second and I ended with 0. This one I'm slowing down and I have a negative acceleration. This one, I have a negative acceleration, but I'm speeding up. The acceleration is in the direction of the motion. If the acceleration is in the direction of the motion, regardless of what sign it is speeding you up. If acceleration is in the opposite direction of your motion, like this one, this is slowing down. It's really important to keep those two things straight. So we have that. I get from here that I have then the slope of a velocity versus a time graph gives us acceleration. What about this area here, is there anything you suppose if I just wanted to look at this little spot here, I want to look at the area under this. I look at that and I say, okay, so this is time, no problem. And this is velocity. Okay, that's just the graph information. Isn't the area of something, well, I can write it up here. Doesn't the area equal length times width? Isn't that true for area? So for the area here, let's see, what do I have? I have length is time. So my total length here is 10 seconds. And my width, well, I can call that width. I could call it length times height. It doesn't matter. It's just a square. So I'm just taking the sides of the square to figure out what the total area is. So this one here, well, let's see, this is 10 meters per second. Is that total height? What happens by units there? I look at this, I have a second on the bottom and a second on the top. So my seconds cross out. And that gives me 100 meters. Oh. So this area here, well, this is my displacement. Now let me frighten you a little bit. When you do calculus, which is what we've just done, this little handy-dandy thing here is called an integral. It's measuring the area under the curve. This fancy thing here, this slope that we just defined is rise over run, and then we figured out what the acceleration was. This thing, this is a derivative. So this would be like dv dt. Oh, which is just that, isn't it? So the one piece I want you to get from all of this is that a lot of people look at this and they're like, I can't do physics with calculus. Well, you just did, and you just did it with a graph. These things, even though they look intimidating, they're nothing more than looking at rise over run, looking at your slope, or looking at the area. I mean, we can get all fancy here. Do you remember what the area of a triangle is? And if you don't, remember you have handy dandy Google, what's the area of a triangle. But if I look here, let's see, we'll just do this one here because I'm running out of space. This is just, this area here is 1/2 base times height. That's the area of a triangle. So I can get that area under the curve. I can solve for that if I want. I can solve for that area if I want. If I want to know what my total displacement is from here to here, then it would be the displacement. I'd measure the area here. So I'd calculate that with 1/2 base times height. And I would add to it the area of that square. So from this little graph, I can get all of that information. It's very exciting.